Okay, let's get on to non-linear substitution. So this is kind of like the more complex application of substitution, but it's still pretty tame in comparison to some of the stuff that we will be getting onto. But non-linear substitution is probably the most common type of substitution you're going to see, mostly in kind of correlation with different types of, or like, sorry, with combination with different methods. So you'll have to do like a question, you might have to use partial fractions, integration by parts, and then also nonlinear substitution. It's kind of like an extra complicating factor that you're likely to see in a complex question. So, when do we use nonlinear substitution? We use nonlinear substitution when the derivative of u, and by u we mean like the non-linear component that we're going to substitute in. If the derivative of the non-linear component would cancel out any x's or any function of x that you don't want. This is a heavy sentence, so I'll go over it again. We're going to use nonlinear substitution when the derivative of our nonlinear component, so in this example here, our nonlinear component is 3x squared plus 1, the derivative of our nonlinear component would cancel out the different function that we don't want. So the function that we don't want here is the x, and our nonlinear component is a 3x squared plus 1. So what nonlinear substitution is about is mostly just recognizing patterns and understanding derivatives. What you need to be able to do is look at an integral, recognize that there are kind of two separate functions. So here we have the root 3x squared plus 1 and the x, the two separate functions, and in this example we have one function being x and one function being cos x squared. We need to look at the two separate functions, and you need to recognize if the derivative of one is going to cancel out the other. So you just need to make sure you're practicing your derivatives and be good at recognizing those patterns. And look at an integral and ask yourself, is the derivative of one of these functions going to cancel out the other? So, ignore these two dot points here for now. These are more tips for complex questions we'll get into later. So, the steps are exactly the same as linear substitution. And we'll get into an example now. But the key difference between, as I said, linear and non-linear substitution is you actually need to like pick which function is going to be the thing you substitute, or which function are you going to let equal u. And the function you let equal u has to be the one that the derivative of would cancel out the unwanted function. Remember, the other function we don't want because it stops us from integrating. Like in these two functions here, we have a quotient and a product, and we don't have a quotient or product rule for integrating in high school maths. They actually do have one in university, I've heard from my friends in maths, but not in high school. So what we need to do is we need to find other ways to do it. And so kind of when we have like this unwanted other function, we don't want that other function because it's creating a product. Like here, we don't want this x because if we didn't have this x, then we wouldn't have a product, and then it would be easy to integrate. Same thing here. If we didn't have this x here, it would be a lot easier to integrate. So let's get into an example, and we'll go back over these instructions and the principles as we go through the example. And then after that, we'll go over the tips for complex questions for like the more high achieving people, or the people who just, I guess, are more interested in maths. So remember, we want to pick the function that we substitute for u. we want the derivative of that to cancel out the other function. So this example here is actually a little bit tricky because you might think that we need to let u equal x, or that we need to let u equals cos x squared. But you actually need to think about it a little bit harder. You want to pick the thing that if you found the derivative, it would cancel out the other thing. So what I recognize here is that we have an x and an x squared. And the derivative of x squared is x, or rather 2x, but it has an x in there. So that can cancel out the other x that we have. So we'll get into it, and we're going to follow the same steps as our linear integration example. So remember, our first step is to let u equal the thing that we're substituting. So I'm going to let u equal x squared. And now we need to find the derivative of u with respect to x. And for our second step, remember, we need to isolate dx. Exact same steps as linear substitution, we need to isolate dx. So we're going to get dx equals du over 2x. Now for our third step, we need to substitute dx and u into our original integral. So we are going to leave the x there because we didn't have anything for that, but we have the cos of u multiplied by du over 2x. Now, as you can see here, what we have is a very satisfying occurrence if you do it right. And it's even more satisfying the harder the question is, if you see something that will cancel out nicely, like the x and the x in here. So as you can see, our plan worked out perfectly because we chose our substitution to be something that would cancel out the other unwanted function that we had. We have now been able to cancel it out, and now the only thing that we have to integrate is cos with respect to u, which is really easy, right? That's just in our formula sheet. So we've really simplified everything a lot more for ourselves. Now, our integral is going to be a half sine u plus c. And remember, our fourth step is to substitute our u back in. So we're going to be left with a half sine x squared plus c. Brackets there. Yeah, that's pretty much the gist of it. Again, it's exactly the same steps as linear substitution. You just need to have that extra mental step of thinking, is one of these functions going to cancel out the other one that I don't want? Okay, we're going to quickly go over the tips that I had for more complex questions. Again, because we don't have time to go over all examples for all of these tips, if you are interested in them, I would recommend making yourself a question or finding a question in your textbook that kind of matches these tips to practice yourself to better your understanding. So the first tip that I had was, if you have a product of cos and sine where neither has a power, other than 1. So they both have a power of 1. It's just like cos something and sine something, or only one has a power, then this is another circumstance where you would use nonlinear substitution, right? Because the derivative of cos is sine. So that's going to cancel it out. You know what I mean? Because like sine and cos are like their own derivatives. Um, if you let one of them be the non-linear component or equal u, then the derivative is going to cancel the other one out. Of course, this is only going to work if the cos and sine that you have the same angle. If it's the cos of x and the sine of x, or like the cos of 2x squared and the sine of 2x squared, and so on. But yeah, just recognizing that because cos and sine are like kind of their own derivatives, that you can then use nonlinear substitution. Another case that you can use nonlinear substitution is if you have a trig product where only one of them has a power other than 1. So if you have like cos squared multiplied by sine, right? Only one of them has a power other than 1, and that's the cos squared. If you have that, then you need to make the one with the power u. So in this case, if we had cos squared sine, then we would let cos squared equal u. Okay. Another tip on when we can use nonlinear substitution is if you have a product of sec x squared and tan x with any power, n, you can use a substitution u equals tan x because the derivative of tan x is sec x. If you haven't gotten to this kind of differential stuff yet in Specialist, don't stress too much. The whole point of these complex tips that I had for you guys is just kind of instances where if you have like the product of a function with its derivative, then obviously you're going to let the original function equal u. It's just recognizing those patterns of when you have like a function and the derivative of that function is like similar or the same as the other function that you don't want. Okay,